Welcome back to another HVAC-Engineering-Techie channel training video. Today is another course on our controls modules, and it's constant volume air handler unit control system sequences. So this shows you the basic sequences for constant volume air handling units. Remember that this is the channel that talks all things HVAC, engineering design, construction equipment systems, test and balance, controls, efficiency, and performance. So don't forget to become a subscribing member if you're not already. You do that by hitting the subscribe button down below. Give me a thumbs up if you like the video. Those things are free to you, cost you nothing. No one will bug you. There's no responsibility for that, except it helps me because Google uses that data to evaluate my videos. And I would appreciate that because it keeps me on the air. All right, let's get started on constant volume air handling sequences. Thanks. All right, so now we're just going to go and review the other control training videos, what's available to help you. We'll go through them quickly. If you've seen other videos, you've seen this before, but we'll go quickly. C1 was the control system basics that you need to understand the language and the acronyms for controls. DDC control network devices explains the devices that are used to communicate around the network. And in the DDC control architecture, C3 lays out the networks and shows you how we use networks. C4 is DDC control components and devices. C5 is DDC control installation and wiring. Tells you what's important about wiring and how to make sure that the wiring doesn't degrade the performance of the system. C6 is water cooled central plant control system sequences. C7 is hot water central plant control sequences. C8 is chilled water control system sequences. And this is C9, which is constant volume air handler control system sequences. C10 is VAV air handler control system sequences. C11 is outside air handler unit system sequences. C12 is tuning DDC loops. C13 is how to select and size control valves. C14 is how to select and size control dampers. C15 is pneumatic controls. Now, I know you say we don't use pneumatics anymore, but we actually do use some components of pneumatics, and this lays out what those are. Now, all these sequence ones are a deep dive into the control sequences for energy performance and for standard performance. Where there get to be fancy reset sequences, we're using ASHRAE Guideline 36 to help us get to those points. So hopefully these will be helpful for you, these 15 videos. Control sequences. The main technical resource used in this presentation is ASHRAE Guideline 36 2024, High Performance Sequences of Operation for HVAC Systems. Also utilize the standard industry practices. Now, standard 36 is a really high quality, good sequence primer, but unfortunately it's very, very hard to read. And the reason is they put everything that's possible to happen. So they put in a sequence and then they have all these adders depending on what you're going to do. And that's what makes it very, very difficult to read. It's just not a sequence. It's, if you're going to do this, well, then you got to do that. And it goes on and on and on. It makes it very difficult. So I've gone through and tried to pull out what we need for these sequences I've given you. Now, these sequences I'm covering are, of course, not all the sequences. There are many more sequences available. But these are the standard ones, standard practical ones that have been used for many years. And some of them are newer, but basically it doesn't have a sequence for every possible kind of system. That would be impossible. Normally, the design engineer describes their desired sequence of operation in standard language on the drawings or in the project specifications. Now, there's possible issues with designers creating sequences. One, if they create a new innovative sequence that's never been used before, there could be problems because in doing sequences, there's a whole bunch of hidden things that affect you don't think about until it's too late, and then you got to do it in the field. Standing in the field in the middle of the night or middle of a hot day with a bunch of unhappy customers is not the time to figure out, oh, well, that ain't going to work. Why did we do that? So really, new sequences, innovative sequences are difficult. Now, there are some reasons we need some innovative sequences if we're doing things that we've never done before in mechanical systems. But I got to tell you, there's pretty much a sequence for everything you could ever possibly need that's been out there, has been vetted, and are existing. There's very, very few new ones. But most young engineers that come up believe they need to create a new sequence to make it much better the way they want it to run. which could be problematic. Incorrect logic for logic components. There's certain kind of ways you do sequences. You remember that programmers don't speak English. I mean, they speak English, but they don't program in English. They need to program in the syntax of their software. And so there's many things required that aren't in the English language one. Too complex for successful implementation. I see this sometimes. I see sometimes young engineers will create a sequence that's near impossible to write because it's way too complicated. I mean, I've seen them where they say if 10% of the boxes are doing this, do that. If 20% of the boxes are doing that, do something different. 35%, and it goes on to the right, and it would take a programmer forever to write that sequence. And if you have a very complex sequence, remember, not only can the control programmer create it, but the operators will never be able to keep it operating, and that's really the problem. So the KISS principle, keep it simple, stupid, still applies to controls. As simple as possible to still do the job you want, to give you high quality. Now, the control submittals are supposed to include a rewritten sequence that includes all details required to produce the desired sequence, or supply a manufacturer standard sequence that has been fully vetted for actual performance. Unfortunately, what actually happens most of the time, I'd say 99% of the time, the control contractor simply cut and paste the engineer's plain English language sequence and puts it in his submittal and says it's the sequence we're going to do. Unfortunately, and the reason he does that is he doesn't want to be disapproved by the engineer for not doing his exact sequence. Well, as a commissioner, or if you're going to test a system, it won't work because he's not going to program that. He's going to program it with the syntax he requires. He's going to need input points, inlet points. He's going to need the exit points. He's going to need timers. He's going to need limiters. He's going to be a whole bunch of things, that sequence he needs. The engineer doesn't know any of that. He's just writing that in his sequence. So you're pretty well guaranteed that the sequence the programmer is going to write will not match exactly what the engineer has said, and you won't quite know how to test it. So that's why it's important to have an actual sequence, written sequence of exactly what the programmer is going to program in there, and not just say, going to be sort of like this. All right, what's sequence standards for air handler components? We got operating schedule, occupied schedule, and unoccupied schedule. We get space environmental set points for occupied and unoccupied conditions. Remove set point dead band of 1 to 3 degrees. Now, dead bands, there are some green building movements that demand to have 4-degree dead band, and that's a problem. The way it is a human being can almost not feel 1 degree. Almost nobody can feel really, truly 1 degree. 4 degrees, everybody can tell. So if you do a 4-degree dead band, you're going to have a lot of unhappy customers in the building. It's going to get warmish, it's going to get coldish, it's going to get warmish, it's going to get coldish. It's too much. 4 degrees is too much. Here's the standard default space temperature sequences from Guideline 36. For occupied space, 75 degrees for cooling. This is the standard default space temperature set points. This is from Guideline 36. Occupied space, cooling is 75, 50% relative humidity. Heating is 70 degrees and 35% humidity. The humidity unoccupied is 90-degree temperature in cooling, 60 degrees in heating. These are a little aggressive. 75, originally when we had energy issues, we used a set point of 78 and a temperature of 72. Now, they've pushed these up a little bit. They pushed the temperature down 75, and the temperature has been pushed down. The cooling set back at 90 degrees, I think, is too high. Now, I normally use about 85, 84, 85. The key number here you need to take your building and calculate how much energy it takes to get the building from 90 degrees down to 75 degrees. And is that amount of energy less than to keep the building at 90 degrees all night long? Or if it's 84, then you compare those two until you see which is the most energy efficient. If it takes less energy to pull that building down from 90 degrees to 75 degrees than it does to keep it at 85 degrees, and to pull down from that, then you make your decision on that. Unfortunately, it's hard to make a rule of thumb judgment because every building is different. It's a really poorly constructed building, then this is going to be better. If it's a very tight building, very energy, it's very very well insulated, this may not be a good thing. So you have to, and if it has high mass, I guarantee you this won't be a good thing. Because if it has a real high mass and that the walls all get to 90 degrees, it takes a lot of energy to pull it down. So all those are considerations you have to actually use the building to tell. Mechanical rooms, 85, 65. Operating rooms, 65 degrees across the board. Data centers, 75 degrees. Now, this is older data. We used to be told by the computer guys that their processors actually need 75 or 68 degree even there, but cold air at the chip level, because the chips need cold air to function. And so we would pump 68 degree air into space, so the rooms were always really cold for operators trying to get that air to be below 75 when it gets across the chips. Well, now they're telling us that the new processors can do 95 degrees at the chip level, so we don't have to do 68 in space. So we can do 75 degrees to the computer rooms and be just fine. That's something that's changed. Standard CO2 room limits, occupied space is 1,200 ppm, or one of the sequence I prefer is to measure the outside air and add 800 parts to it. And if it's 400 outside, that'd be 1,200 parts per million. But what happens is 1,200 parts per million, a lot of people have been using 1,000 parts per million. I've seen some 900 parts per million. That's actually too low. You're going to burn a lot of energy for no benefit to the customers. And that's, I think, by people who believe that CO2 is a pollutant. And, of course, it's not. It's one of the gases we need to survive. 900 is not a problem. 1,200 is not a problem. Actually, we've measured in classroom settings up to 3,500 with really no ill effect. So this 1,200 parts per million is not that bad, and you should use that if you're trying to use energy efficiency. 900 you could use, but you're going to be spending a lot of money for it. Start-stop is control sequence standard components for air handlers. Start-stop, sequence condition for startup, sequence condition for shutdown, optimal start conditions, optimal start conditions, optimal stop conditions. And what this optimal start is the system remembers, normally it's the last 7 days, of how long the system took to get from unoccupied set point to occupied set point. And whatever that time is in optimal start, then it will use that time when you start up the system again. So if you're in optimal start, it will say, okay, it only took 15 minutes to get the temperature, so we don't need to start up an hour or 2 hours before. We can start up 15 minutes before and be right on time. It'll do that automatically, and the optimal start's a very good thing. It works very well. Optimal stop, we don't use it, and the reason is not because it doesn't work. It does, and it does exactly the same thing. The system remembers how long it takes to get from occupied set point to unoccupied set point, and it turns the system off early. So if your building quits the day at 6 p.m., and it says it takes me 30 minutes to get to unoccupied temperature set point, I'm going to turn it off at 5:30. The problem is that air conditioner systems make a lot of white noise in the building. And when you shut it down, the people say, what happened? Where did that noise go? That I didn't even realize was there. And that causes you all kinds of issues because they also now know what a quiet building is without the noise of the HVAC system. So we don't use that because we get a lot of complaints if we use it. It'll save a little energy, but not worth the grief. Morning warm-up. Do we need a morning warm-up? Do we need a warming cool-down? So do we need to have specific... Now, optimal start will actually do the same thing, right? But if it turns out that optimal start takes an hour and a half to get there, maybe you want to get there sooner. So you could do that by using a morning warm-up and a morning cool-down, which has special sequences to do that. Temperature control, of course. Temperature control sequences are both cooling and heating. Temperature control reset sequences, if we're going to reset the sequence. Humidity control sequences, humidity reset sequences. We're going to reset those. Building pressure control, return air fan control sequence, relief damper pressure control reset sequences. All right, control sequence, standard air handler components, outside air flow control, return air fan control sequences, relief damper pressure control reset sequences, CO2 control, outside air relief damper control for CO2, economizer dampers. We're going to use the outside air to cool the building during the winter. Alarms that we need, that operator needs, operating data trends that the operator needs to run the system, and operation reports. These are all part of the sequence requirements. Now, a lot of people in their sequences will say the system should be capable of being alarms, capable of operating data trends, and capable of operating reports. But that's not correct, because the operators need certain data to run it, and if you don't provide them in the sequence, and you don't provide them, the control programmer doesn't provide them, then the operators have to learn the system, get familiar with the system, figure out what they need, and then try to program it themselves. It's not really well for them to do that. They shouldn't do that. We should provide them the ones they need. Now, if they want others, they can always add them, but you should provide the ones that really are important for them to operate their systems. Okay, most important items for energy reduction: loop tuning, all loops fully commissioned and tuned. Temperature and pressure reset sequences fully commissioned and tested. These are the things that actually provide energy efficiency. And if you let somebody blow these out for whatever reason, then your energy goes out the window. And this is why persistence systems is not well maintained, because people say this is too much trouble, I'm just going to blow this out. It's causing a problem, or I don't have the right temperature, so I'm just going to blow these out. And it will cause you to lose your temperature efficiency. Space temperature and humidity set points maintained. It's really important that you have a standard policy for space temperature and humidity. So if you have one zone at 72 degrees and the next zone right next to it at 75 degrees, they're going to fight each other with that temperature. So there should be a policy about having a standard temperature, unless there's special rooms that require something. But in general, you don't have temperature differences all over the place because someone complains, so we set that temperature different. You need to have a policy to set it all the same. And that really applies to humidity. Vapor pressure will go right through a wall. So if you have humidity levels different and you have the capability of doing dehumidification, you're going to spend a lot of energy. Occupancy schedule strictly maintained, so we don't be changing schedules all over the place. Operations committed to maintain these above. So the operators have to be willing to do these to keep the persistence in place and the system operating correctly. All right, let's look at two-pipe fan coil unit. Real small unit, just a fan coil unit. You can see it has a fan that blows through. Normally these little fan coils are blow-through, and so they blow through a coil. And they're small, so we normally have strip heaters. It might have a hot water coil for heat, but this one has a strip heater. So it has an outside air damper that we close and open when we operate, and we have a room sensor. Now on these diagrams, I show these room sensors as hardwired to a point, but basically most of these room sensors will be LAN sensors, so they will have a sub-LAN that goes up here, a little network, so they can, across this point, we get temperature, we get fan control, we get a lot of things, we get override control. There's things we get from here that don't take other points to burn. This is a standard system, so this is pretty easy. Our point list is DO1 is a starter for the supply fan, DO2 is a contactor for the electric heater, it's a single stage heater. DO3 is the actuator, so this is a two position, it's open and closed. And we do that so that we don't get any outside air during unoccupied periods. Analog outputs is the cooling coil control valve. This is an analog device. Digital inputs is starter supply fan status. We have a current switch on this thing. And then a float switch. This one specifies a float switch in the pan to know if we got a clogged coil, a clogged pan drain. So that's for an operator to get up and make sure that's clean so it doesn't ruin a ceiling tile. Analog inputs, a room temperature sensor, and a supplier temperature. So we have a supplier temperature. Now, why do we put a supplier temperature on a small fan coil or any kind of air handling unit? And basically it's because it's the cheapest, most reliable, most effective status point for the unit. Is the unit working or not? So if there's a room temperature problem, you say, wow, we got a high temperature in that room or low temperature in that room. The next thing you check is what's the temperature of the supply air. And if the room's really cold, and the heater should be on, and you check the supply temperature, it's cold too, it means probably the electric heater's not working. So you can do testing like that, and cooling, same effect. It's too hot in the space, supposed to be cool, and you check the supply air temperature, and it's cool. Well, that's working, so we got to figure out what else it is. Anyway, it's a status point. It's the most effective status point. Cheap. There are other status points. You can check your current switch. Is my fan running? It doesn't work very well if the fan's not running. Okay, control sequence. The fan coil unit shall be enabled or disabled based upon an occupancy schedule. The supply fan shall run any time the unit is in the occupied mode at the design CFM is set by tab. If after 5 minutes the fan current switch status point indicates no airflow, then stop the fan and alarm fan failure. Cooling control. During the occupied mode, the cooling valve shall modulate to maintain the supply room set point, temperature set point. During unoccupied modes, the cooling and valve shall modulate to maintain the unoccupied room set points. And here's kind of a diagram, operation diagram. We have a 75-degree set point in the room. And as it gets warmer, this cooling valve begins to open until it gets to 78 degrees. And this is the maximum, will be maximum open, so that's our maximum cooling. And on our heat strip, we have a one-stage heat strip. So if the temperature falls to, this is 69 degrees, the heat strip comes on. And the heat strip stays on until it gets to 73 degrees. 73 degrees. Now this has a 2-degree deadband, which is fine. But you realize that this is not going to provide really even heating control, because it's going to clear the 69 to 73, and it's going to go on and off and on and on. If you wanted more precise control, then you could put this on an SCR, a Silicon Control Rectifier, which instead of a contactor, it's a device that will modulate this electric heater. And you can modulate this electric heater like this if you have an SCR on it. During the unoccupied mode, this is heating control. The electric heat coil shall be staged to maintain the occupied room temperature set point. And then during unoccupied, it'll do those. Outside air control. When in the occupied mode, the outside air damper will open to the minimum outside airflow position as set by tab. Anytime the supply fan is running, the outside air damper shall be closed when the unit is in unoccupied mode and the supply fan is off. So this is how that outside air works. It just opens and closes, and the balance guy has to set the stops at what the open position should be. Close is full close, but that's the open position. Okay, monitor points. Monitor the room temperatures continuously. If the room temperature is above or below set point for more than 3 degrees for more than 15 minutes, send a level 3 trouble alarm. And remember, the trouble alarms, number 1 is a life safety trouble alarm, which means all the bells and whistles alarm should be going off because it's a life safety issue. 2 is a level 2 is a alarm that means an operator needs to get up out of the chair and go do something now, because it's going to cause problems immediately. Number 3, a level 3 double alarm is an alarm the operator said, I know I got a problem here, I'll need to fix it, but it's not immediately critical. It is something we need to take care of, but it's not, I don't need to go running out of my chair right now to do that. I can schedule that to be done. And level 4 is just a trouble alarm that means nothing. And so basically, you really shouldn't have any trouble for it. Level 4s, they're not necessary. Monitor the condensate pan fluid. If a high water level is detected, it's at level 3 trouble alarm. Now, you might want to make that a level 2. It depends on what's underneath the unit. Data trend room temperature, supplier temperatures continuously with an interval of 15 minutes. So we want to know what the room temperature and the supplier temperature is for a tool for the operators to use. Data run time if the all motor that run the motor, resettable by operators for maintenance. All right, let's go up to a little bigger unit, 2-pipe constant volume air handling unit. So this is a two-pipe, still 2 pipes. It only has 1 coil. It has a heat strip, but it has a full economizer and a return fan. So what happens here is the return fan sucks the air out of the room, and it runs through this return damper, through the filter systems, through the cooling coil, to the blower, to the heater, and out to the space. Now, if you're in an economizer, then this damper closes, this one opens, this relief damper opens, the outside air opens, and what happens is the outside air comes in and cools the space. Return fan takes it and pushes it out of the space. So this is how an economizer works, and why we have it. These happen to be filter switches. Now, this is the only unit I've shown filter switches, even though they will be on most units. And the reason is filter switches don't work that well. And on a constant volume, they can work, but they're not well maintained. They don't usually work very well. The correct way to do filters is have experience in the building and decide that the filters need to be changed at a certain interval. And the reason I say that is because, just think about it. If you're an operator and you've got 30 air handlers in your building, And you have filter switches, and you're going to change when a filter gets inserted. So one day, okay, we need to change this filter. So you change that filter. 2 weeks later, okay, now we need to change this unit's filter. No, wait a minute, we got to change this filter. So you have a continually process of changing filters, or you never know where. That's not how they do that. They normally change all the filters at the same time, and many people have a subcontractor do it. They do it themselves. To do that, you need to come up with a schedule. Okay, we've tested these. These get dirty enough to change in 3 months. So we need to change the pre-filters every 3 months. The final filters we can change every 2 years. Something like that. So you have a schedule. You can watch the filter switches for anything that's important. Maybe there's some big dust storm comes up and fills your filters. But you need to do it on a schedule. Now the other thing too is that we're not in VAV, but when you get to VAV, they don't work at all. Because as the airflow goes down, the switch goes, the pressure goes away, because it's not a direct proportional relationship. So you can't use them on VAV. You can put them there, but they don't mean anything. So I've only shown the filter switches here so you can see what they look like, how they work, but really we don't use them very often. Here's the point list. DO1 is fans, supply fan start stop. DO2 is a return fan start stop. DO3 is electric stage 1. DO4 is electric stage 2. Analog outputs is a cooling valve, the outside air damper, and the relief air damper actuators, because these have to modulate. Digital inputs is supply fan status, return fan status, pre-filter switch, and the final filter switch. And these are these filter switches. Now what you have to do is you have to set these up and adjust the trip point so they're at the correct point you want the filters to report that they're dirty. Analog inputs, temperature is room temperature, and again, I show this as a single point. Might actually be a sub-network coming into the system. Temperature, supply air temperature, return air temperature, low temperature, sensor temperature, which is a freeze stat. Temperature sensor of outside air temperature and humidity outside humidity. These may be global points coming in from a central plant, or they may be coming in from a weather station. That's the point list. Let's look at a standard sequence. The air handler should be enabled and disabled based upon the occupancy schedule. The supply fan shall run any time the unit is in the occupied mode, and the design CFM are set by tab. If after 5 minutes the fan current switch status point indicates no airflow, then stop the fan and alarm failure. Now up here in all of these sequences I've saved by occupancy schedule. Now, the programmer should really ask the owner for him to give him the schedules of the building so he can program them into the system and not rely on an operator to have to do that. Now, the operator will need to be changing those in the future, but when the building starts and the system starts, the programmer needs to input those. Return fan. The return fan should run any time the supply fan is running. If after 5 minutes the fan current switch status point indicates no airflow, then stop the fan and alarm fan failure. Cooling control. During the occupied mode, the cooling coil valve should modulate to maintain the occupied room temperature set point. During unoccupied modes, the cooling coil should modulate to maintain the unoccupied set points. Okay, and then of course we have heating control. During the occupied mode, the electric heaters shall be staged to maintain the occupied room set points, and the same for unoccupied set points. So here it is again. It looks similar to the other. We have a 75-degree room temperature, and the cooling coil will open as it gets hotter in the space. And this is a little bit as it goes down from 75 to 71. Stage 1 will go on, and stage 1 will heat the air up until it goes off at 73 degrees. So this one will give a little better performance than the fan coil before, because we don't have quite so bit difference. And it gets real cold in the space, and stage 1 is on, and it still gets colder. It goes to 69, and stage 2 will come on. And stage 2 will come on and go off at 71. And so these are trying to fill it in. Again, if you wanted tighter control in this, you could put an SCR on the strip heater, and you could just modulate it like it was a valve. So that's possible to do. Outside air control. When in the occupied mode, the outside air damper shall open to the minimum outside air position is set by tab anytime the fan is running. The outside air damper shall be closed when the unit is in the unoccupied mode or the supply fan is off. Tab shall set the return air fan flow and outside air damper position to provide minimum outside airflow for design ventilation air to provide adequate building pressurization. So now none of these are VAV. These are all constant volumes, so this has to be set up by the balance contractor. So what the idea is we want this pressure in the room to be just slightly positive. We don't want to blow the doors open, and we don't want it being negative. We don't want to suck in dirt and debris in the building. So what he does, he sets the supply fan up and balances all that, and then he goes to the return fan and he sets this up in speed so that the supply fan, the building pressure is where they want it. And then they have to do the thing again when it's in economizer mode. They have to do it all over again to rebalance these. But that's basically the process of making sure the room has the correct pressure. Okay, dry bulb economizer code. So remember again, when we're doing this, if the outside air temperature is between 40 and 70 degrees and the outside air temp is 10 degrees below the return air temp for more than 15 minutes, enter economizer mode and modulate the outside air relief and return air dampers to maintain the room temperature set point. During economizer operation, the cooling valve shall be closed. If the room temperature rises more than 3 degrees above set point for more than 5 minutes, return to normal operating mode. Tab shall be set the return air flow and outside air damper. Return damper and relief damper position to provide design building pressurization within the economizer mode. So he has to set it again for economizer mode. And normally it's not too difficult. You have to do that. But the key to this whole thing is that this be zero pressure. And what that means is that we don't want the system running so that the plenum area for the intake is positive pressure, because then this becomes a relief damper. And we don't want this negative, then it becomes an outside air damper. So basically we have to balance this so that this is zero pressure right here. So the fan is pushing out the air here, and this fan over here is sucking it in. So this is negative pressure, this is positive pressure. And that's somewhat tricky for a balance guy, but it's due. Now this is that diagram, this economizer. This is going to control to set point, and it will modulate from 72. The relief damper will be closed, and the minimum outside air damper will be in a bit of a position. As it gets warmer, the outside air damper will open, and the relief damper will close. Will open also. These follow each other. I'm sorry. The return damper, they will be open and closed, and it's reverse acting. This damper is reverse acting of this damper. So we can see that goes that direction. Typical control sequence alarms. Monitor points, trend alarm, monitor room temperature continually. If the room temperature is above or below set point by more than 3 degrees for more than 15 minutes, send a level 3 trouble alarm. Monitor supply and return fan status continuously while the unit is running. If any fan status indicates fan failure, send a level 2 trouble alarm. Data trend room temperature, supply and return air temperatures continuously with an interval of 15 minutes. Data trend outside air temperature and humidity continuously with an interval of 15 minutes. Data trend outside air, return and relief air damper positions anytime the unit is running with an interval of 15 minutes. Data log the time of all motors reset by operators or maintenance. We're going to keep track of how the run time of the motors. Okay, let's talk about a 4-pipe constant volume air handling unit. This is a little bit more complicated unit. You see, this unit still has a supply fan, return fan like the other, but it has a cooling coil, and it has a heating coil downstream of the cooling coil, and it has a preheat coil. So this would be a system that is in a very cold temp climate, and they need to preheat the air during the winter because they still need air conditioning and heating. But they need to pre-cool it because it's too cold coming in. And then we have a coil downstream, so we can actually dehumidify with this unit if we need to. So other than that, it's a standard unit like last one. The control points list is the starter, supply fan, start-stop, return fan, start-stop. That's the digital outputs. The analog outputs are the cooling coil valve, the outside air damper, relief damper, return damper, the hot water coil, and the preheat coil. So now we've got a lot more valves. Digital inputs is the supply fan status, return fan status. These are the current switches. Analog inputs is the room temperature, room humidity, supply air temperature, cooling coil leaving temperature, return air temperature, return air humidity, outside air temperature, and outside humidity. And the reason we need these points is because we're going to be doing some dehumidification, and we may even be doing an enthalpy economizer. We'll talk about that in a second. Okay, the air handler should be enabled and disabled based upon an occupancy schedule. The supply fan should run anytime the unit is occupied. Mode at design CFM set by tab. If after 5 minutes the fan current switch status point indicates no airflow, then stop the fan and do a trouble alarm for the fan. Return fan. The return fan shall be run anytime the supply fan is running. If after 5 minutes the fan current switch status point indicates no airflow, then stop the fan and alarm fan failure. Return fan speed should be adjusted so it operates at a flow equal to the supply fan status minus the outside airflow rate set by tab. So what I'm saying there is that the balance contractor slows this fan down so that the difference between these two airflows is the amount of outside air they need. And this is how they get the correct amount of air induced into the system. And they figure out what that air is because the engineer will tell them what the ventilation air requirement is, and then they need to adjust it slightly more to make sure they make up for any exhaust, any relief, any building leakage to get a slightly positive, and not by slight I mean 0.015 or something like that. 0.02 or 0.015 is enough. You don't need a whole lot, but a little bit. Okay. So optimal start. The control system shall data log the time it takes each day from the fan start at the beginning of the occupied period until the room temperature reaches set point. Each day, the control system shall average these times for the last 7 days of operation and use this number to set the start time so the room temperature is at set point at the occupied start time. So that's that optimal start. Cooling control. During the occupied mode, the cooling coil valve should modulate to maintain the occupied room temperature set points. And it'll do that for the unoccupied too. Heating control. During the occupied mode, the hot water coil shall modulate to maintain the occupied room temperature set point during occupied modes, and hot water coil valve should modulate to maintain the unoccupied set points also. So here we are. So here we have a 75-degree set point, and we're going to let the cooling coil go from that to 78 from full open. And we're going to put a 1 degree dead band here. So at 74, the hot water coil begins to open, and at 72, it'll be full open. And of course, this will maintain this dead band, and this will be it won't be like a digital start stop. It gives you a nice analog, smooth flow of temperature. Preheat coil. So, okay, so modulate the preheat hot water valve to maintain the preheat set point temperature of 45 degrees, measured at the leading side of the cooling coil. If the cooling coil outlet temperature drops below 38 degrees, stop all fans, close the relief outside air damper, and open the reheat and chill water coils valve to 100% and send a level 2 freeze alarm. So what we're going to do, the way this works, is this cold air is coming in from the outside, and there's this, we're getting return air, but we also got cold air coming in. It hits this coil, and if it's below 45, this coil comes on to maintain 45 degrees here. Now, the reason we measured here is because we already have a temperature sensor here, and the cooling coil set point is always above 55. So if we set it to 48 or 45, then we can use this because the cooling coil won't be off. It'll be off. And so we can just let this heat go through there. And the second thing we're using this preheat for is so we don't have to have such a huge coil here. So this may see 45 degree air coming in. It can now raise that on up to the temperature it needs to do the job. And the engineer will have sized these coils to do that. And here's the preheat deal. So if we get to 50 degrees, it's closed. But if it's 40 degrees, it will be open and we'll be trying to maintain that 45 degrees. Now remember, these ranges I've just picked, there's no magic beyond these. They could be closer. This could be 40. This could be 2 degrees this side, 2 degrees this side instead of 5 degrees. Those are just whatever you decide and how quick you want it to respond. Outside air control. When in the occupied mode, the outside air damper shall open to the minimum outside air flow position as set by tab anytime the supply fan is running. The outside air damper should be closed when the unit is in the unoccupied mode or the supply fan is off. Tab shall set the return air fan flow in the outside air damper position to provide minimum outside air flow for the design, ventilation, air, and to provide design building pressurization. That's what I've already talked about. So he's going to adjust this so he's got the correct building pressure. All right, so now we're going to do dehumidification control. So if during the occupied mode the room humidity rises above 60% for more than 5 minutes, place the cooling coil into dehumidification mode. When the room humidity drops below 45% for more than 5 minutes, return to normal temperature mode. In dehumidification mode, modulate the chill water valve to maintain the cold deck leaving temperature to maintain 50% room humidity, and modulate the hot water valve to maintain the room temperature set point. So what happens is when we have high humidity conditions in the space, we drop the coil down cold. Now, a lot of sequences just drop it to 55 degrees. Well, that's okay, but I prefer to let's drop it to whatever it needs. If it doesn't need 55 degrees, let's not drop it that cold, or 50 degrees, or whatever it needs. So we just simply say it's going to run this coil down to maintain 50% of the space. And when the space gets to below 45, it's going to turn it off. So that's how the dehumidification works. All right, so now we have a full enthalpy controller, and that's why we have all these humidity sensors around the space. Now, the one thing about humidity sensors is they get out of calibration much quicker than temperature sensors. So if you're going to have an enthalpy economizer, you need to calibrate your sensors at least every 6 months. If not, you're going to end up wasting energy because they'll drift out, and unfortunately, it's a major component to your calculation. So the control system shall calculate the outside air and return air enthalpy from the dry bulb temperature and relative humidity sensors. If the outside air enthalpy is 4 BTU per pound less than the return air enthalpy BTU per pound for more than 15 minutes, enter the economize mode and modulate the outside air relief and return air dampers to maintain the room temperature set point. During economizer operation, the cooling coil valve should be closed. The room temperature rises more than 3 degrees above set point for more than 5 minutes, or if the outside air enthalpy is less than 3 BTU per pound of the return air enthalpy, then disable economizer mode and return to normal operating mode. Tab shall set the return air fan flow and the outside air damper, return damper, relief damper positions to provide design building pressurization while in economizer mode. Now, you'll see some engineers like to run the cooling coil as second stage in economizer mode. I do not like to do that. And the reason is that these engineers assume that the temperature control and the enthalpy control is very tight, very accurate, and will always provide the economization. But the truth is, both dry bulb and wet bulb temperature sensors tend to drift. And as they drift, you get too close. And what happens, you end up recooling. So the outside air is a little too warm, and the cooling coil is dropping it down. And you don't want to do that because now you're double dipping. So what I like to do is, if you're in economizer, let's use economizer. When it's right at that shoulder load, let's just turn it off. There's too big a chance of wasting energy. Let's just turn it off and go back to air conditioning, because remember, the central plant is really, really efficient when it's that cool outside. So you're getting really high efficiency anyway. So the economizer is just the next step to help, but let's keep them separated enough so we don't need two-stage. A two-stage, just so you know, one thing, over the 50 years I've been working, almost every building I've ever entered, the economizer is not working. What happens is, a problem happens, the operators turn them off because they're fighting them. There's something wrong with it. Well, it's because the sensor or the logic is not correct and it's too difficult to handle. They just turn them off. So most all of them are off when we get into a building. So just remember that. Trying to set them up as dual stage is tricky at best. Freeze protection. If the low temperature sensor drops below 40 degrees for more than 5 minutes, close the outside air damper and send a level 3 trouble alarm. If the low temperature sensor drops below 38 degrees for more than 15 minutes, shut down the supply fan, return fans, close the outside relief damper, open the cooling coil valve and full open, and send a level 2 alarm. The system will require an operator to verify that the freeze condition is no longer present before clearing the alarms and resetting the unit operation. So again, level 3, something he needs to know about. Level 2, he needs to get up out of the chair. So that's what those levels are. Okay, typical control sequence, monitor points of the trend, same as the others. Monitor the room temperature continuously. If the room temperature is above or below set point by more than 3 degrees for more than 50 minutes, level 3 trouble alarm. Monitor supply and return fan status continuously while the unit is running. If the fan status indicates fan failure, send the level 2 trouble alarm. Data trend room temperature, supply air and return air temperatures continuously with an interval of 15 minutes. Data trend outside air and humidity continuously with an interval of 15 minutes. Data trend outside air and relief air damper air position anytime the unit is running with an interval of 15 minutes. Data trend the outside air temperature and preheat coil valve position anytime the unit is running with an interval of 15 minutes. Data log runtime of all motors resettable by operators for maintenance. So these are the things the operator needs to see and operate his system. All right, constant volume dual ducts. We got two more kinds of air handlers. We got dual duct air handlers. Now, dual duct air handlers were our early attempt at VAV, and we can provide variable temperature to the space, many zones, but with still constant flow. So here's how this works. We have this air handler, just like the others. It's got a supply fan, return fan. It's got a full economizer. It's got filters. But it has a cold deck section and a hot deck section. And this blast plate, it's just a plate with holes in it, is here designed to back pressure this flow to break up any stratification across the cooling coil and to force air up to the hot deck. So what we do is we have two duct systems. We have a cold duct system and a hot duct system that run out to the space. And then we have dual duct boxes which take air from both systems and mix that air for the room. So they change the temperature by adding more return air or more hot deck air to less cold deck air or vice versa. And these are very good systems. They work very well, but they're very expensive because you're running two duct systems. So they're not very popular with people who have budget constraints. Now, many colleges and universities use them continuously because they're very valuable, and they will do this actually VAV, both of them. But in normal office buildings, these are not used anymore, just too expensive. Digital output, supply fan start-stop, return fan start-stop, analog outputs, cooling coil valve, hot water coil valve, outside air damper, relief damper, return damper. Digital input, supply fan status, return fan status. Analog inputs, cold deck temperature, hot deck temperature. Return air temperature, low temp sensor, outside air temperature, outside humidity. And that's the point list for our dual duct air handling unit. This is the dual duct box. Digital inputs is room sensor override button. Analog inputs is a temperature sensor for the room temperature. And again, this may be a network connection. And that's how the box operates now. In the old days, these are pneumatics. We had one pneumatic actuator, and we had both dampers on the same shaft, but set up opposite. So when one opened, the other closed. So now when we have electronic actuators, we have to make sure one is opposite direction to this one. So the same signal drives both dampers, but one in the opposite direction. So they will always be opposite of each other. Sequence and control of the box. The dual duct box shall modulate the cold deck and hot deck dampers in reverse of each other to maintain the room temperature set point with constant air volume to the space. The air handler should be started on a schedule. The supply fan shall run anytime the unit is in the occupied mode. The design CFM is set by tab. After 5 minutes, a current switch status point indicates no airflow to stop the fan and alarm failure. Return fan. The return fan should run anytime the supply fan is running. After 5 minutes, a fan current switch status point indicates no airflow. Then stop the fan and alarm fan failure. The return fan speed shall be adjusted so it operates at a flow equal to the supply fan minus the outside airflow rate by tab. Then again, that's to induce the right amount of outside air. Cooling control during the occupied mode. The cooling coil valve shall modulate to maintain the cold deck temperature set point during unoccupied mode and cooling flow. So what's different about this is that it's not doing room temperature. This is doing actually the cold deck temperature. And the dual duct box is being controlled by the room temperature. So this actually is a set point of 60 degrees, so it's going from 57 to 63. And of course the valve is opening and closing to maintain that temperature. Heating control during the unoccupied mode, the hot water cold deck. The hot water deck coil shall modulate to maintain the hot deck temperature set point. And again, maintain the unoccupied at the same time. Now you notice the set point is 80 degrees. And why that is we're trying to economize energy. So what we want is this hot deck to be return air temperature. So we can use the heat of the lights, heat of the people, and heat of the load of the building to provide the heat we need. Now that means that if it's not enough, we'll reset this up to be hotter when it needs it. But normally we want it set so that we're doing all the cooling with the cold deck and we're not reheating very much, because reheating is wasting energy. All right, temperature reset control. Here we go. Anytime the unit is running, we use a trim and respond logic loop with a 3-minute time interval to evaluate the system reset request to reset the cold deck and hot deck temperatures. Reset the cold deck temperature by the following reset logic. If any dual duct box cooling damper is greater than 99% for more than 6 minutes, send 3 change requests. If any dual duct box cooling damper is greater than 97% open for more than 3 minutes, send 2 change requests. If any duct box cooling damper is greater than 95% for more than 3 minutes, send 1 change request. If any duct box cooling damper is less than 95%, don't send any request. Reset range for the occupied cold deck shall be from 55 to 70. So we have a cool deck clear to 70 degrees when we don't need it during winter. And so this is the cold deck. And then we have a hot deck reset, and we will talk about that in a second. So this is the cold deck parameters, which means we have a set point of 60 degrees on the cold deck, and it goes from 55 to 70. Our time delay is 6 minutes. Our deadband is 6 minutes. Our interval is 3 minutes. Our ignored request is 3. And again, they recommend this be about 3 or 10% of the connected boxes. We're assuming we have about 30 boxes. R is the request, change request. Set point reset, which is to drive the temperature lower. We're going to use a minus quarter of a degree, so we're going to go down real slow. Now we're going to have a reset maximum of -1. So if we have a whole bunch of resets, it'll change that temperature fairly quickly. It'll go down 1 degree every 3 minutes. And for trim, we're going to go up 1 degree every 3 minutes. So the formula is if the resets are greater than the ignored request, then the temperature reset equals R minus Ri times res V, this value. So if you have a net of 4 resets after you subtracted 3, the ignored request, then it would be 4 times 0.25, which would be 1, which is maximum. So if you have more than 4, it doesn't matter. It's only going to let you change -1. Now again, these set points are selected by me to give the correct response to the system. If you need quicker response, you need to change them. If you want slower response, you need to change them again. So what we're doing here is we're using a real small value to go up because that is increasing energy, and we're using a larger value to go down. And then I always use a chart to figure that out. So this is the parameters down here, and you can read that. Here is my little chart I use to tell how responsive the system is. Now, what normally happens is you get these requests come in, and then they're filtered. And so we spend the first 6 minutes not doing anything because we have a deadband of 6 minutes when we first start. And then it goes to 3 minutes. 3 minutes now, it says, okay, I've got some requests coming in. So I need to reset. So reset it down, and it turns out that it's 4. We have more than 4, so it sets it down, and it keeps setting it down and setting it down. And then you see it started to slow down. We don't have 4, now we only have 3. So we reset 0.75, and the last one, it only does 2. Well, that's because we're getting down to minimum. We're not quite to minimum yet. So at this point, the resets change, and it doesn't have any requests. So now we start going up 1 degree till we get to the maximum temperature of 70 degrees. Now, it will never operate like this, but what I'm doing is trying to tell what is the maximum time limits to get from here to here. And you see this was only 21 minutes, and my parameters try to do this within a half hour. What I'm trying to say is you don't want the customer to say, wow, it takes a long time to change the temperature, nor do you want it too quickly because it'll overshoot and it will use more energy. So these are the values, and I've used 20 minutes, 30 minutes, something like that as a reasonable amount of time. If you start out at this temperature up here, this is starting at 60 degrees, and we need colder air. It can get colder fairly quickly. 20 minutes will cool it down. People will wait 10 or 15 minutes, not a problem. An hour, they won't wait that, so it's too long. And then this time here is just information, because this will never happen. You'll never have a condition where you need low, cold air, and then all of a sudden you need really warm air. It would be really weird for that to happen. So normally this goes around and goes up 1 or 2, goes down, goes up. It kind of meanders around in real life. But I'm setting this up to prove what these maximum times are. Because before I got into this kind of sequences using the request, we just did it with just looking at the damper positions. We would overshoot and they'd go too fast sometimes, and then way too slow sometimes. It'd be an hour and a half trying to change temperatures, which was a problem. So this is why using the request where you can speed up the response, sometimes slow it down, is a very good thing. And here's the temperature reset for the heating side. Reset the hot deck temperature by using the following reset logic. If any zone room temperature is below set point by 3 degrees for more than 3 minutes, send 3 requests. If any zone room temperature is below set point by 2 degrees for more than 3 minutes, send 2 change requests. If any zone temperature is below set point by more than 1 degree for change request. If any zone temperature is at or below heating set point, send 0 change request. Reset range shall be hot deck temperature from 80 to 120. Now you can also do this just like you did the cold side, but look at the hot deck damper. The same way. I probably should have done that to make it a little simpler. And this is the hot deck parameters. Our set point's 80, our range is 75 to 120, so we can get hot if we need to really heat the building. We have the dead band, we have the 3 minute, and we have the 3 request ignored. And we're going to go at 0.5 degrees up, and we're going to maximum of 3 degrees, and down at -4, because we're trying to keep this energy low. We don't want it there very often. I didn't mention it before, but the tolerances for all these, both cooling and heating, is the time limit's half a second, temperature is 1/10 of a degree, and the speed is 0.5% speed. So these are the tolerances that we're using for these systems. And this is my chart for the hot water. So if we come out of the hot water at 80 degrees, and we're getting a bunch of reset requests, remember the first 6 is ignored minutes, the next 3 minutes, and we start going up at 3 degrees. And you can see going up until it gets to here, and then it's our maximum, and then it starts coming down. Again, these timers, this one was 39 minutes, and this was 24 minutes. And to me, that puts me right in that half-hour time. If we wanted it faster, we can make it faster. But this is a spot to start. If you need to adjust it to get a little fine-tune the system, you can do that. Outside air control. When in the occupied mode, the outside air damper shall open to the minimum outside air flow position as set by the tab. Anytime the supply fan is running, the outside air damper shall be closed when the unit is unoccupied mode or the supply fan is off. Tab shall set the return air fan flow and outside air damper position to provide minimum outside air flow for design ventilation and to provide building pressurization. Dry bubble economizer. Going back to a dry bubble economizer on this one. If the fans are operating, the outside air temperature is below 40 and 70 degrees, and the outside air temperature is 10 degrees below the return air temperature for more than 15 minutes, in air economizer mode and modulate the outside air relief and return air dampers to maintain the room temperature set point. During economizer operation, the cooling coil valve should be closed. If the room temperature rises more than 3 degrees above set point for more than 5 minutes, return to normal operating mode. Tab shall set the return fan airflow and the outside air damper, return damper, and relief damper position to provide design building pressurization while in economizer mode. And here's this chart of the economizer. So when we're cold, the room temperature is cold, and the relief damper and the outside air damper are closed. The outside damper is in minimum position, and as they get warm, they both open up, and the return damper is running opposite to those. And this is how these economizers work. Freeze protection. If the low temperature sensor drops below 40 degrees for more than 5 minutes, close the outside air damper and send a level 3 trouble alarm. If the low temperature sensor drops below 38 degrees for more than 15 minutes, shut down the supply fan and return fans, close the outside and relief dampers, open the cooling coil valve to full open, and send a level 2 alarm. The system will require an operator to verify the freeze condition is no longer present before clearing the alarm and resetting the unit operation. So now you can use, this is the cold temperature here. It's going to tell us we're going to freeze alarm. That we want to prevent that. The hot water coil can continue to operate because it's not going to freeze. So we don't need to overheat this space. If the fans are off, we can open the water here also. But freeze alarms are a problem. We need to make sure we don't burst any coils. Monitor points, monitor the temperature continuously. The room temperature is above or below set point for more than 3 degrees. For more than 15 minutes into level 3 trouble alarm. Monitor supply return of fan status continuously while unit is running. If any fan status indicates a failure level, a level 2 alarm. Data trend room temperature continuously with an interval of 15 minutes. Data trend the cold deck and hot deck to return their temperatures continuously while the unit is running at a 15-minute interval. Data trend outside air temperature humidity continuously with an interval of 15 minutes. Data trend outside air relief air damper position anytime the unit is running with an interval of 15 minutes. Data log runtime of all motors resettable by operators for maintenance. All right, the last air handler, multi-zone air handling units. And a multi-zone air handling units was also one of our early attempts to give variable flow or variable temperature to a space. These are still used once in a while if you have a really large zone. So if you have a zone that you can't do with a VAV box, if you have a 10,000 CFM zone and you have 3 or 4 10,000 CFM zones, then you can either do a whole bunch of VAV boxes or you can use a multi-zone. And I see these in certain specified buildings still today. This has to be a constant volume and not a VAV volume. You can't make these VAV also, but this is constant volume. So we have a return fan, supply fan, just like the others with a full economizer, and we have a cold deck and a hot deck, just like the dual deck we had. However, this is not running 2 ducts throughout the space. What it has vertical dampers on the outlet of both the heating deck and the cold deck, and the damper is connected reverse. So these are on the same shaft, and as one opens, the other closes. And then we run a duct to every zone from these positions. So these are long, skinny ducts that they transition out to space. And then we have so this is a 3-zone multi-zone. You see it has 3 room sensors, and it has 3 damper sections in here. The way this works is normally these dampers come out with damper plates every 6 inches, or maybe every 4 inches, and then they gang together as many as they need for a zone. And then they put an actuator and you link them together so you get the zones. And that's how you set the zones up in the field, because these are all different. When I was a designer back in the day, we used a lot of these, and I've had up to 11 zones. And you want to try to design the 11 ducts coming out of an air handler. It's very, very difficult. So I'm glad these are not around much anymore. They're still here, but they're not much. Multi-zone points, supply fan start-stop, return fan start-stop, analog outputs, cooling coil valve, hot water valve, outside air damper, relief damper, return damper, zone 1 damper, zone 2 damper, zone 3 damper, digital input, supply fan status, return fan status, analog inputs, zone 1, room temperature, zone 2, room temperature, zone 3, room temperature. Forgot to do that. Cold deck temperature, hot deck temperature, return air temperature, low temp sensor, outside air temperature, and outside humidity. And these are the point lists for a multi-zone unit. Typical control sequence. The air handler should be started and able to disable based upon occupancy schedule, just like everything else. Supply fan shall run anytime the unit is in the occupied mode and design CFM is set by tab. After 5 minutes, the fan's current switch status point indicates no airflow. Stop the fan and do an alarm fan failure. A return fan. The return fan should run anytime the supply fan is running. If after 5 minutes the fan current switch status point indicates no airflow, then stop the fan and alarm fan failure. The return fan speed should be adjusted so it operates at the flow equal to the supply fan minus the outside air flow rate as set by tab. Cooling control. During occupied mode, the cooling coil valve should modulate to maintain the cold deck temperature set point. During unoccupied modes, the cooling coil valve should modulate to maintain the unoccupied set points. And here again, my set point is 60 degrees. And it goes up to 63 and down to 57. So we use a 6-degree deadband, a 6-degree throttling range. Maybe too high. Maybe you only want to use 4 degree or something like that. Those are settable by you, actually. Heating control during occupied mode, the hot water coil valve should modulate to maintain the hot deck temperature set point and the same during an unoccupied. And here's an 80 degrees. So we're doing this again. We're trying to maintain the hot deck temperature as a return air temperature so we can use the heat of the building to heat wherever we need to. And of course, if that's not enough heat on any zone, then we have to reset the hot water up. So temperature control resets. So now we're going to reset both the cold water and the hot water to be able to do the load we want. So anytime the unit is running, use a trim respawn loop logic with a 3-minute time interval to evaluate the system reset request to reset the cold deck and hot deck temperatures. Reset the cold deck temperature by following the reset logic. If any zone damper is greater than 99% open for cooling more than 6 minutes, send 3 change requests. If any zone damper is greater than 97% open for cooling for more than 3 minutes, then send 2 change requests. If any zone damper is greater than 95% open for cooling, then for more than 3 minutes, to send 1 request. If any zone damper is less than 95%, don't send any request. Reset range for the occupied cold deck should be 55 to 70 degrees. And this is the parameters again. So we have a 60-degree set point, 55 to 70 throttling range. We have a 6-minute delay start. We have a 3-minute time interval. We have 3 ignore requests. Our request action is minus 0.25 degrees for cooling. Maximum is -1. And reset, our trim logic is +1. So the formula is if the resets are greater than the ignore request, then it's R minus IR times the res value. So again, if you had 4 net value of resets, because you had 7 and you subtracted 3 and you had 4, be 4 times 0.25, it ended up being -1, which is your maximum limit. So if you had 8, it wouldn't be 2, it would be 1 because we have a limit on it. And then on the others, if you have no reset request, then you start changing it 1 degree every 3 minutes. So that's the way we go to cooling. And here's the cooling reset logic again. So we start here at our 60 degrees and we start going down because we got reset request. And we get down and then we can go back up again just like we did before. And the time variables are very good. These are too small for me to read. This is 42 minutes up and 21 minutes down. Down is much more important than up. Up doesn't mean anything because the boxes can switch all to the heating side if we need it, if it's too cold. So we want to go up because we want to save this energy, but it doesn't matter if it goes. We could change this. We could get this more aggressive. We could make this 1.5, cut it down a little bit. We make it even 2, cut it down a lot if you want to. But this is within realm of the cooling of the space. Reset the duct temperature by using the following reset logic. This is the hot water deck. If any zone room temperature is below set point by 3 degrees for more than 3 minutes, send 3 requests. If any zone room temperature is below set point by 2 degrees for more than 3 minutes, send 2 change requests. If any room set point temperature is below set point by 1 degree, send 1 change request. If room temperature is at or below heating set point for 0 change request. Reset range for the hot water deck temperature should be 80 to 120. And here's the parameters for the hot deck. Set point is 80. Remember, we're trying to use the return air, and the reset range is 75 to 120. Dead band is 6 minutes, 3 minutes for interval. 3 is our ignored request. And our static pressure reset is 0.5 inches. Hot deck, I'm sorry. Temperature is 0.5 degrees up, and our maximum is 0.3 up. And our reset trim is -4. So if resets are greater than the ignored request, then the temperature is R minus IR times res value, this one. If the R is less than 1, which is 0, I mean, if you have no reset request, then it's -4. So we're going down quickly. So these are a little bit more aggressive, and so its temperature is this way. So if your reset comes on at this 80 degrees, and we need it hotter, it will start going up. And it took 39 minutes to get to maximum, and it took 24 minutes to come down. So it's coming down a little bit faster on the hot side. And this again is to save energy. We want to get down quickly. That's why we set these up to do that. And so this will be a hot deck reset. When the outside air control, when in the occupied mode, the outside air damper should be open to minimum outside airflow position set by the tab. Contractor, anytime the supply fan is running, the outside air damper should be closed when the unit is in the unoccupied mode or the fan is off. Tab shall set the return air fan flow and outside air damper position to provide minimum outside air flow for design ventilation air and provide design building pressurization, just like the other systems. Typical control sequence, so it's a dry bulb sequence, and basically the fan operates and the outside air temperature is below 40 degrees and 70 degrees, and the outside air temperature is 10 degrees below the return air temp for more than 15 minutes in economizer mode and modulate the outside air. Relief and return air dampers maintain the room temperature set point. During economizer operation, the cooling coil valve should be closed. The room temperature rises more than 3 degrees above set point for more than 5 minutes. Return to normal operating mode. Tab shall set the return air fan airflow and outside air damper, return damper, and relief damper positions to provide design building pressurization while in economizer mode. And again, this is the chart. So when it's cold, these are closed. When it gets warmer, they both open, the relief and the outside air. And the return air damper is opposite those. So now you could use here, for this economizer, I'm using room temperature. You would have to, an average of the room temperatures, something like that. Or you could high select or low select the room temperature to get that mode. So dry bulb economizer is pretty easy. Now you can set these temperatures. This 10 degrees is pretty big because I like it. When I start economizer, I want to make sure we got lots of cold air to use it. And then as it gets lower, we'll turn it off. But a lot of people like to start very close, like 4 or 5 degrees, but I don't like that because then it can go in and out, in and out, in and out. And I would rather have it start and stay on. Economizer work really well, especially if you have 24-hour operation, because the nighttime is always suppressed and it's cold at night, so you can use more economizer during that period. Freeze protection: if the temperature sensor drops below 40 degrees for more than 5 minutes, close the outside air damper and send the level 3 trouble alarm. If the low temperature sensor drops below 38 degrees for more than 15 minutes, shut down the supply fan and return fans, close the outside air relief dampers, open the cooling coil valve to full open, and send a level 2 alarm. The system will require an operator to verify that the freeze condition is no longer present before clearing the alarm and resetting the unit operation. And here is the temperature control zone. Each zone room temperature sensor should modulate the multi-zone damper that mixes flow from cold to hot decks to maintain the room temperature set point. So these dampers, here's the hot deck and cold deck, are actually hooked on the same shaft. So as it gets colder, the cold deck is closed and the hot deck is fully open. And so it's mixing air here as it goes down. So this is the way these dampers work. Monitor points. Monitor the room temperature continuously. If the room temperature is above or below set point for more than 3 minutes, 3 degrees for more than 15 minutes, send a level 3 trouble alarm. Monitor supply and return air fan status continuously while the unit is running. If any fan status indicates fan failure, send a level 2 trouble alarm. Data trend room temperature of each zone continuously within an interval of 15 minutes. Data trend cold deck, hot deck, and return air temperature continuously while the unit is running in a 15-minute interval. Data trend outside air temperature humidity continuously with an interval of 15 minutes. Data trend outside air, return air, relief air damper positions anytime the unit is running with an interval of 15 minutes. And that's the regular alarms and trouble things we want. Data trend runtime of all motors, resettable by operators for maintenance. All right, so now we're going to talk about constant volume air handler set point change suppression. Now what we're doing here is it says anytime a temperature set point is reset greater than or equal to 1 degree, start a suppression timer that prevents the more reset requests or set point alarms for 3 time intervals. If after that the reset condition remains the same or is greater, extend the suppression timer another 3 time intervals. And if after that the reset condition remains the same or is greater, then extend the suppression timer another 3 time intervals. Then end the suppression timer. So what we're trying to do here is to keep the resets from multiplying when it's a timing issue. So what happens, say you have a VAV box in a room and the room temperature is warmer and it needs to be colder, so we're going to reset the supply duct temperature down so we get colder air in the space. So what happens is that condition exists, so it sends us some requests. Then we go into our interval, and if the next interval, if the room hasn't changed temperature, then that box is going to send us resets again. And if it doesn't do it again, it's going to send us again. So if we don't suppress it, it will continue to send us requests and can even do alarms. So it could do multiple alarms. Well, we don't want that for at least, we'd like it to be out there for at least 30 minutes, somewhere around there. It could be less, but right around that time period. So we give it time to react, because it could be that the room has a lot of mass and it takes the air some time to change the temperature in the room. So we want to give it a chance. So we're going to give it this 30-minute time period before we let it go back to alarm and do set requests. Now, what happens, this will slow down us driving all the way to the reset all the way up or all the way down. So what we're trying to do is not let that happen. That's what we're doing. We're only doing room temperature because that's the one that will affect energy the most by requiring more and more energy to that air, even though it may not be changing. So it's going to drive the set point way up. We'd rather have it modulate that slowly instead of ramp it up all the time. So that's what the suppression all is about. Now, you can suppress other things like duct static pressure, but I don't normally do that because it's really tightly contained and it can be affected very, very quickly. So it won't have like a broom can, a large mass. It will happen very, very quickly. So I don't see any need to put a suppression on that. You could do room humidity, but my sequences that are in this video don't actually reset humidity like this temperature reset. It's a different kind of reset altogether. It doesn't need to have this suppression. And that's it. I know this is a little redundant as you go through each air handler, but they are different. And this kind of just gives you an idea how they actually operate and how sequences should operate. Now, for every system and every air handler, you have to kind of adjust to these sequences to match what you actually have. And I just tried to show you different aspects of different systems so you can figure out what you need for your specific sequence. I hope this was helpful. I appreciate you watching, I really do. And I hope you guys have a great day, and I'll catch you in the next one. Thank you.